Thank you for the introduction. Can you all hear me? Yep. Okay, so I'm going to dim the lights so you can see the slides better. So I'm telling you about the connection between cosmology and particle physics. So let me first define what I mean by these cosmology and particle physics. So what is cosmology? So cosmology is basically, the study of cosmology is basically concerned with a number of things, like what is the universe made of, what is its structure, the origin, and where it's heading. Now obviously these are age-old questions, and many people in the past have attempted to answer them in one way or another. But when we talk about cosmology these days, in other words, modern physical cosmology, it's an empirical science. And what it means is that we collect data and we try to come up with a theory that can explain the data. And when I say theory, what it means is that we postulate principles and then we formulate them in mathematics. So mathematics is important in the game. And then we try to explain the data, or we try to predict signatures for new observations so that we can collect the data from the observations and then see if we can confirm the theory or refute it. Okay, so it's fully consistent with the scientific principle. Now, I'm a theorist, so I'm going to be mainly talking about the stuff that is on this side of theory. So let's look at what actually underpins what kind of principles underpins modern cosmology. So the central tenet of cosmology is the cosmological principle, and basically it states that on large enough length scales, the universe is homogeneous and isotropic in space. Another way to put it is that we're not special. We don't live in a special place. Now, if you look at the two words here, homogeneous and isotropic, they sound like the same thing, but actually they are not the same thing at all, because homogeneous means same everywhere, whereas isotropic means same in all directions. So if you look at these three pictures over here, the first case is isotropic, because it's the same in every direction. Here's this little blob here is supposed to be the galaxy that we live in, the Milky Way galaxy. And if you look in all directions, things look the same, but obviously you don't have homogeneity. The second one here has homogeneity, but these planes here are all flying in one direction, the same direction, so you don't have isotropy. Only this last picture here actually shows a situation that conforms to homogeneity and isotropy. Now, is it a good assumption? This should be, because if you look at, you look into the night sky and look at how stars and galaxies are distributed, and this is a picture of such a distribution. It's measured by the 2-mass redshift galaxy survey, and it shows you the local galaxy distribution. Each dot here is a galaxy. Then you can see that they are pretty uniformly distributed, provided that you go on sufficiently large scales. And then when I say large scales, what I mean is about 300 million light years. Now, I don't know if you're familiar with the units of light years, but basically, light travel, the speed of light is the fastest speed that we know that is allowed in nature. And 1 light year is the distance that is covered by a light wave in 1 year. Okay, so 300 million light years, it's an enormous distance scale. That's a black bit here, that's just the Milky Way, basically, because you can't, when you do a survey, we're living in the Milky Way, so we cannot look behind the Milky Way. So that's why you have this black region. But otherwise, the northern hemisphere and the southern hemisphere, they look more or less the same. There are some fine structures, but on the whole, the gross structures, they're similar. So homogeneity and isotropy are good assumptions. Now, you probably all know about the general theory of relativity, and that is the theory that was postulated by Einstein, and it's a geographical theory of gravitation. And so basically what happens is that Einstein proposed to look at gravity in a completely different way. So, so what you do is that you think about space and time as sort of the same thing. Now we know space is three-dimensional space that we live in. Time we always think of as a separate entity. But here what we do is that we lump space and time together and think about a space-time manifold. Okay, the manifold, it's a jargon, but you can just think about it as maybe like a sheet of paper or just something, okay? Now, if we're looking at empty space, then the space-time is flat. That's a situation that is the simplest. And if you have a particle that is traveling in this empty space, then it will just go in a straight line. And that is consistent with what we know already from Newton's first law, which says that if you have a particle or something that is traveling at constant velocity, it's going to keep going in a straight line and maintain that constant velocity. Okay, so that describes the situation. Now, things change when you actually put some stuff into the space. Now, what I mean by stuff is just something with an energy or some mass. Okay, I don't specify exactly what kind of stuff it is, but I'm just going to put this stuff into space. Then what happens is that this stuff is going to curve the space-time manifold. Okay, and you can actually express this entirely mathematically rigorously with this equation over here. This is Einstein's equation. And basically what you have on the left-hand side is a bunch of terms that describe the curvature of the space-time. So this curved part here, it's encoded in these symbols on the left-hand side. And on the right-hand side, you have some other symbols here that actually describes exactly how the stuff that you have is distributed in your space. And importantly, what this equation says is that if you have stuff, it's going to bend your space-time, and also if you have curvature of space-time, then this curvature is also going to determine the path that the particles are going to travel on. Okay? And the rule of thumb is that your particles always travel on the shortest path, no matter what kind of space-time you have. And these are called geodesics. And it's a bit like looking at a flight path. So if you're thinking about, this is a trip I'm doing in a couple of weeks, going from Seattle to Munich, I think. Yes. And now if you look at this map, you think a straight line is just like that, going across, but that is actually not the shortest distance on the surface of the Earth, because the Earth is curved. Okay, it's a sphere. If you travel on the surface, you always travel on these curved paths. And actually it turns out that the shortest distance between this point here and that point is this long arc here. So that's why when we fly in the northern hemisphere, you almost always fly over the North Pole, pretty much the North Pole. Now, okay, so that was the case of the general curved space. So what happens, what we want to ask now is what happens if you have stuff in space, but this stuff is homogeneous and isotropic. Okay, that's the cosmological principle, homogeneous isotropic. We're going to put some homogeneous isotropic stuff in space. Now, that's exactly what these four gentlemen here considered back in the 20s and the 30s. And what they found is that if you have a homogeneous and isotropic distribution of some energy in space, then what necessarily happens is that the space will expand. So, and it's described by this equation called the Friedmann equation. It basically says that the expansion rate square is determined by the energy density of the stuff that you have in the space. There's also a term, extra term that depends on the intrinsic spatial geometry. And if you want to visualize it, you can think about like a raisin bread or something, and where each raisin here could be like a galaxy or something, and your universe is the bread itself. So the raisins themselves don't actually expand, but the distance the distance between each pair of raisins would increase due to the expansion of the bread. Okay, so that's the analogy of what's happening in the expanding universe. Now, this expansion has been observed, and it was actually first observed by Edwin Hubble. Actually, I don't think he was actually aware of the work of those of Lemaitre and Friedmann before, but anyway, he did this observation. What he did was to look at galaxies, and he considered the distance between two galaxies and how fast they're receding away from each other. And what he found was that actually the relative velocity between two receding galaxies and actually follows this really simple linear relation compared to the distance between the two galaxies. It's V equals hd, and it's known as Hubble's law. And this Hubble's law here is actually completely consistent with the Friedmann picture we have on the expansion of the universe. Okay. Now, another consequence of spatial expansion is what is known as cosmological redshift. And so this little schematic here shows you the expansion of space, and this is time in the upward direction. And what happens is that if you have, let's say, a light wave being emitted from a galaxy over here, then the expansion of space is also going to stretch out the wavelength of this light wave. Okay, so that by the time the light wave actually gets to the second galaxy over here where the observer sits, it's going to be longer than the original wavelength. And that's the redshift. That's what we call redshift. Okay? Because if you look at visible light, red light has a longer wavelength than blue. Okay? So we call it redshift because the wavelength is increasing. As it turns out, this redshift doesn't only apply to light rays, it also applies to matter waves, and basically anything with a momentum. Will suffer this kind of cosmological redshift. Now, so we have expansion, we have redshift. What kind of conclusion can we draw from these two things? Well, you think about it, the universe has been expanding, which means that the further back in time you go, the denser things are. And also you have the redshift. Okay? The redshift stretches out the wavelengths, and you know that the wavelength is inversely proportional to the frequency. Now, if you think about Planck's law for the electric effect, the frequency is basically something related to the energy. Okay? So that means that the further back you go, the more energetic things must have been. In other words, things must have been a lot hotter, because temperature basically is a characterization of the amount of kinetic energy something has. So if you extrapolate really far back in time, then you're going to reach a point where things are of infinite density and infinitely hot, and that's the Big Bang. So that's what we mean when we talk about the hot Big Bang model. Okay, it's this kind of picture over here. Now, it's always a question of what really happens when you have infinite density and temperature, and that's a difficult question to address because when you're actually at that kind of density, all kinds of physical laws that we know about will break down. So it's probably has to do with, probably can only be resolved if we think about quantum gravity and the like. But still, even if we ignore the fact that there might have been a singularity or maybe no singularity, still you have this picture of a really dense universe sometime in the early times and an expansion. Okay, so that's still okay, singularity or not. So we have this really dense place then in early times. Then what it means is that it also begins to matter exactly what kind of stuff there is in the universe that actually is causing this expansion in the first place, and also the kind of forces that this stuff feels. Okay, and so here we come to the next topic, the fundamental forces of nature. So we're slowly moving into the particle physics regime. Now, we know a lot of forces. That we talk about a lot of forces in everyday life, but actually they all boil down to just 4 forces. So we have the strong force, that's the force that binds a nucleus together. We have electromagnetic forces, that's when you have electric charges, and that's something we're quite familiar with, and it also is the force that binds atoms together. We have the weak force, and that is responsible for radioactive decay, or decay of a neutron into a proton, for example. And fourthly, we have the gravitational force, which we have already spent some time discussing. Now, as said, the gravitational force, the state-of-the-art theory is general relativity, which I introduced earlier. The other 3 forces turn out to be all basically described in what is known as the standard model of particle physics. Now, you've probably heard about the standard model of particle physics, and it's usually presented to you in this form. This is the particle spectrum of the standard model. So there are leptons and quarks. The quarks are the ones that form, at least the up quark and the down quark, they form the nuclei, and they feel the strong force. And you have the leptons over here that don't feel the strong force, and then you have these gauge bosons, which are responsible for carrying the forces, the weak force, the strong force, the electromagnetic force. We also have the Higgs boson that was recently discovered at the Large Hadron Collider at CERN, and that's the complete particle spectrum of the standard model. But probably, for me anyway, as a theorist, I like this better. I like this picture better because this picture here shows you all the interactions that you have between all the various particles. Because the standard model of particle physics in the end is a relativistic quantum theory that describes how particles interact with each other via the strong, weak, and electromagnetic force. And this actually is the what we call the Lagrangian for the standard model, and it encapsulates all of this physics that is here on this in this picture. Okay, in a really shorthand form, but still, it's technically correct. Now, what does this mean for cosmology? So if I take all these forces and all these particles that we know about from the standard model, and then we embed it in an expanding universe setting, then we arrive at this picture. So you still see the expansion as represented by these lines here. That's the expansion. And you go back in time, and you find that the universe was really hot, was really dense, and the temperature and the energy scale is very high. So this is E, here's the energy. Now, there are a few things that are few predictions that we can make already in this picture. And the first I want to talk about is nucleosynthesis. So nucleosynthesis is the process by which light elements up to lithium-7 were formed in the first minutes after the Big Bang. And basically it was studied by these guys. And what they looked at was a network of reactions, of nuclear reactions, such as this network over here. And they looked at how all the light elements can be formed simply from protons and neutrons. And they did it in a setting, in an expanding universe setting, in the first 3 minutes after the Big Bang. And what they found is that if you follow this rule, this nuclear networks rule, then it turns out that most of the normal matter that we will find today in the universe must be in the form of hydrogen and helium. That's 99% of the normal matter that we find. And 25% of that is helium-4 by mass. Okay? And this number has been confirmed. So this is really the first really successful prediction of this kind of subatomic physics in cosmology. Okay? The prediction of 25% of helium-4 by mass. A second phenomenon that was also studied in the early days, in the 40s and the 50s, is the formation of the cosmic microwave background. And that happens actually about 400,000 years after nucleosynthesis. And what happens is as follows. So here we're looking at nuclei and electrons. And if we let the universe expand and let it cool, then at some point it's going to cool to a temperature below about 300 degrees Kelvin. And this is important because when you are at these kind of temperatures that are sufficiently low, then the free electrons and the nuclei can combine, okay, and form neutral atoms. And this is important for the physics of photons in the early universe, because photons, that's basically a light particle, a light ray particle. Now they scatter very effectively on free electrons, but they don't scatter so well if you have neutral particles, okay? Because the photon likes to scatter off things that are charged, basically. So something that is neutral, they don't like scattering off things that are neutral. So this effect of forming neutral atoms means that at very early times, when you have a lot of free electrons around, the photons will scatter all the time so that the universe is opaque to the photon. However, once the universe cools down to a low enough temperature and you start getting neutral atoms, then the photons don't scatter anymore and the universe becomes transparent to photons. So it's like, if you imagine that we are here and we're looking back in time, then this neutral atom forming stage, where the photons also stop scattering. That's sometimes called the last scattering surface, because that's the last time the photons actually scatter on something. And beyond that, they can just free stream to us. Okay? It's transparent. The universe is transparent to the photon from this point. So in a way, it's a bit like you're looking at into the sky, and it's all clear until you hit the clouds. Okay? The clouds you can think of as the last scattering surface, basically. I mean, the photons can still get through somewhat, but then they will do a random walk, and you can't really see straight through it anymore. So the sky is opaque from the clouds onwards. So I was talking about last scattering. Now the photons that come from a last scattering surface, they are a perfect black body, and the reason is because there was a lot of scattering of the photons on the electrons before the neutral atoms form. And so you have a perfect black body with a perfect Planck spectrum. And what's going to happen next is that, well, the universe keeps expanding, right? And as the universe expands, it's going to stretch out the wavelengths. So initially, your perfect black body spectrum of the photons would have a temperature of 3,000 degrees Kelvin, because that's basically the temperature at which neutral atoms form. But after redshifting down to the present time, it's going to have a temperature of only 3 degrees Kelvin. And also the wavelengths would have been stretched out to microwave scale. And that was actually the prediction of these two guys back in '48. And they said that, you know, if you look at this, then we should be able to see a 3 degree background today of microwave wavelengths. And that was discovered, actually, quite serendipitously by Penzias and Wilson. They were actually engineers looking for something else. And they were trying to get rid of some noise in the telescope, but they couldn't get rid of it. And they started talking, asking around, and they realized that they actually discovered something really important for cosmology, for which they actually got a Nobel Prize in '78. So that's good. But that was in the '60s, and modern physics, modern CMB observations have gone a long way. And this is the best, latest measurement of the black body spectrum of the CMB, done with the FIRES instrument on the COBE satellite. And it was led by these two guys, and they got the Nobel Prize in 2006. So this is, I mean, these error bars I'm showing you here have been blown up by a factor of 400. Okay, so this is really nature's most perfect black body that has ever been observed. And the temperature that corresponds to this Planck spectrum here is a little bit less than 3 degrees, and it's been measured to extremely high accuracy. Now, of course, that was just the temperature. And another thing I want to say is that it's the same temperature, which in more or less the same temperature in every direction they look. But actually, there are some tiny fluctuations in the cosmic microwave background. And it turns out that they are actually very important. So the CMB sky that Penzias and Wilson saw in '65 is essentially just 3 degrees everywhere. So okay, it's just all green, same temperature everywhere. COBE came online in '92, and it started seeing these patterns. So the color coding here indicates the fluctuations in the CMB temperature. And these fluctuations are really, really tiny. They're 1 part in 100,000 or so. And then WMAP, that was in 2003, you can see even better resolution of these temperature fluctuations. And the latest instrument to map out the CMB sky is the Planck mission of the European Space Agency. So this is a Planck satellite. It was launched in 2009. And so basically it traveled to the L2 Lagrange point. And from there started mapping out the CMB sky. So, huh?
That's not a real picture.
Well, it's not a real thing, no. This is an artist's impression of what happened. I mean, they didn't send a camera up there to follow the Planck satellite. Okay, so it's scanning the sky and all around it. So you end up getting a sphere somehow. And then you stretch out your sphere, and that's the map that you have of the sky. Okay, so this is the kind of the emissions that Planck saw in microwave frequencies, and you know, that's the Milky Way there in the middle, and all this stuff here is basically just what we call foregrounds, the stuff that's there in the Milky Way, which is not what we're interested in. So the first thing that the Planck team had to do is to try to remove this foreground. So first they removed all the individual sources that are emitting in the microwave, and they had to also remove all the sources that are emitting in radio frequencies, and all the dust emissions, so on and so forth. So it's pretty complicated stuff they have to do. You know, they have to know exactly what to remove. And finally, once they remove our foreground, this is what they get, the cosmic microwave background with all the fluctuations. Now, so as I was stressing at the beginning, the central principle underpinning modern cosmology is the idea of homogeneity and isotropy. And this is more or less what we see even like this picture here. And that's good, of course. But what is even better is the fact that there are actually fluctuations in the CMB. And the reason is that now the fluctuations, they are kind of, like, look kind of random, but there's actually a pattern to it. And what you can do, what physicists do, what cosmologists do, is to try to calculate the statistical property of these fluctuations. Things like the mean, the variance, correlations of the fluctuation of the temperature fluctuation at different points. And it turns out that these fluctuations are actually very strongly dependent on exactly what kind of stuff is there in the universe, the spatial geometry, and also the initial state of the universe way back, a short time after the Big Bang. And this is important because it means that by studying these fluctuations, I can actually say I can actually reconstruct and find out and try to answer these questions, which is of course exactly what cosmology is about, right? We want to know what is really going on in the universe. And that's what we found. We call this the cosmic pie. Of course, I mean, there are other probes that have come with this pie before. This is the latest measurements from the Planck mission. And so we found that, what I found is that it's 72% dark energy. There's also some dark matter at about 20% or so. Ordinary atoms make up about 4% of this energy budget. And we also have like less than 2% of neutrinos, which are a kind of elementary particle. And the thing is that these numbers here are about accurate to 1%. So that's really a triumph for observational cosmology. But in a way, it's nice to have these really accurate numbers. But at the same time, they also open up a lot of questions because we still don't really know exactly what any of these things are. In fact, if you look at this pie here, the only thing that we can claim to sort of know about are the atoms. Okay, we don't know what a dark matter is. We have no idea what a dark energy is. Neutrinos, we know a bit better, but still not everything. So that's in the second half of this talk, I'm going to move on to talk about these unknown things. Now, as said, it's often said that we don't understand about 95% of this pie over here. Like we don't understand the dark energy, we don't understand dark matter. That's mainly the 95% that most people talk about. But if you ask me, I would even say that we don't really truly understand any of this pie. And I'll tell you why I think that. So let's first talk about dark matter. Now, so there are two dark things in this pie. One's called dark energy, one's called dark matter. They're not the same thing. They're not the same thing because we know that the dark matter, it's a non-relativistic form of stuff. And non-relativistic means that these are particles that don't travel at the speed of light or close to the speed of light. Okay? We know they're not normal matter in the sense that they're not failed stars or asteroids or things that we just can't see. They're not any of that. They're actually something completely different. And they don't interact much with anything else around them. They don't scatter light, because if they scatter light, we would be able to see them. Okay? So here is a really nice picture of the bullet cluster. And basically, what you see here is two clusters that have just collided. And the pink here denotes normal matter. These are false colors, by the way. The pink here is normal matter, and from looking at the X-ray emissions. And you also have blue, that denotes the dark matter, and they know about the dark matter being there because of gravitational lensing. And that, I don't know if you know about gravitational lensing, but that's something that comes off Einstein's theory of relativity, where if you have a lump of mass and then some light emitting source sitting behind it, then this lump of mass is going to lens the light ray so that instead of it going straight, it will be bent like that. Okay, that's lensing. And the amount of lensing is determined by exactly how much stuff you have, okay, sitting there. So that's your lens. And so from gravitational lensing, they figure that there's some mass over here, and that's the dark matter because they can't actually see it. And what's so nice about this bullet cluster picture here is that this is right after the collision between two clusters. And you have a very clear separation of the normal matter and the dark matter, because the dark matter inside the two clusters, they are just basically flying through each other, yeah, not really feeling each other at all. Whereas the gas here, the normal matter that you observe with the X-ray emissions, they kind of get mixed, yeah, because the normal matter can interact. Okay, so this is one of the strongest pieces of evidence that the dark matter is really not interacting much at all. But so that's what we know, but still we don't really know what it is. Okay, we just know it's dark, it's something, we don't know its mass. And even though it doesn't interact much, it probably does have some interaction, and we don't know what they are either. But we can make some educated guesses, and that's what particle physicists do. Now, and it's not even unreasonable. So let's think about an interaction, some interaction. I don't know what it is. But presumably it has to be weak, because if it's too strong, I would have seen it already. So it's some weaker than weak force. And we have a standard model particle, or actually two standard model particles that are denoted by blue, and that's the dark matter. And it's likely that the dark matter would have some sort of interaction with a standard model, because we do have the dark matter floating around. And so it must have been produced somehow in the first place. Okay? So the production is very likely to have come from some sort of interaction between the dark matter particle with the standard model particles. But we don't really know what kind of interaction it is. So let's look at this. Now, what I'm going to do is to draw a time arrow like that. Now, if time goes this way, then this picture here denotes a process whereby the dark matter is produced by the annihilation of two standard model particles. Okay, so you have standard model going to two dark matter particles. And that's the kind of production mechanism that could give rise to the dark matter content of the universe today. And a lot of cosmologists and particle physicists believe that this is probably what happened in the early universe sometime. Probably somewhere at this time, so when the like maybe 10 to the 10 minus 10 seconds after the Big Bang. Okay, very, very early times. Now, so that was when you draw the time arrow this way. Okay, so what I'm going to do now is to draw the time arrow this way. Then what this diagram here represents is a scattering process, where you have a standard model particle like this going this way, and then you have a dark matter particle also coming closer to a standard model particle, and they scatter off each other. Okay, so that's a scattering process. And this is interesting, because scattering processes enable the dark matter to be directly detected in a laboratory. And so this is what sometimes we call direct detection of dark matter. And this is a reasonable thing to think about, because after all, we do think that we're living in the dark matter halo. Okay, this is like from most structure formation theories. It's we also have a lot of observational evidence that we are living in a dark matter halo. Okay, like that. So we're surrounded by dark matter. And in fact, if you take a glass of beer that's about 1 liter, and that's probably about 3 dark matter particles in there. So what you can do is to just put a dark matter detector in your laboratory, and then wait for a dark matter particle to come scatter off the stuff inside your detector, and it will deposit energy in your detector, and thereby you can detect the dark matter particle. Now, it's easier said than done, because if the dark matter can interact with your detector, practically everything else can as well, right? So these dark matter direct detection experiments usually are done in mines. Okay? The reason is that if you put your detector somewhere down in a mine, then you have a whole heap of earth right above it. And that's really good, because that provides a natural shield for all the high energy particles that might be coming down from the upper atmosphere, the cosmic rays and things like that. You want to block all of those things, because you don't want the cosmic rays to interact with your detector. You only want the dark matter to interact. And so there's several experiments of this sort around the world. And I'm showing you this one here. This is actually just a proposal, but it's hopefully, if it gets funded, it will be the first dark matter experiment in Australia. And the idea is to go to an abandoned gold mine somewhere in Victoria in Victoria, and they put a detector there in this gold mine. And it's actually going to be part of a twin experiment together with another similar experiment in Italy at Gran Sasso National Lab. And so we will have one detector in the northern hemisphere, an identical detector in the southern hemisphere, and try to see if we can actually catch some dark matter particles this way. It's not funded yet, but fingers crossed. I hope it does get funded. It'll be cool. So that was direct detection. Now going back to this picture again, this representation. Now what I'm going to do is to draw the time arrow this way. And then what this diagram represents is dark matter annihilation. So you could have, well actually, sorry, I got it wrong. It should have been The arrow should have been going this way. So you have two dark matter particles annihilating into standard model particles. And that should be happening even right now because we do have a dark matter halo that we're sitting in. So not a lot of, like 3 WIMPs in this 1 liter of volume, but still, every now and then the two dark matter particles can get close enough together and they can annihilate into a standard model particle, and which is represented by this schematic over here. And so they can annihilate and maybe follow with some decays. And what you end up getting at the end of the chain, it's a bunch of positrons, electrons, neutrinos, high energy gamma rays, etc. And so what you can do is to put up a lot of telescopes and satellites and observatories to try to detect these annihilation products of the dark matter annihilation. And actually there's a lot of activities going on right now doing exactly that. So this is the AMS-02 at the International Space Station. They really looking at cosmic rays as a result of dark matter annihilation. The Ice Cube Neutrino Observatory is at the South Pole, and it's really literally a cube of ice. They're using the polar ice cap as a detector of neutrinos. And they basically drew a lot of holes down in the ice cap and put a lot of photomultiplier tubes there to pick up any signals that you have of neutrinos going through the ice. That's also Fermi. Large Area Telescope that's looking at high energy gamma rays, but all of these things are really there to look for annihilation products of this dark matter annihilation process. Now, lastly, let's get back to this picture again, and that's a dark matter production. So as I said earlier, the dark matter probably was produced sometime very early in the universe via annihilation of standard model particles into two dark matter particles. So what we can do now is to try to recreate this event now in the laboratory. And you can do that if you have a really high energy collider to accelerate the particles up to very high energies and then do the collision. And that's exactly what is happening at the Large Hadron Collider. So this is at CERN in Geneva. And basically what it does is that you have you inject a couple of protons, well, proton beams really, into a collider. So you go through a few pre-acceleration processes to kick them up to higher and higher energies. And then eventually you feed them into the LHC ring, which is basically this ring here. And that's Lake Geneva over there. And that's the LHC tunnel. And accelerating your the protons. And basically this accelerator is like a series of electric fields and magnetic fields which kind of kick the charged particle along. If you have a charged particle, you put it in an electric field, it would be accelerated. That's what's happening. And there's several crossing points in the LHC tunnel, and they correspond to several experiments. The ATLAS experiment, which is actually the collaboration that produced this video. There's also the CMS experiment, and basically what they do is to look at how the two protons that are circulating around in different directions and how they collide together, and as a result of this collision give rise to all these particles. Okay? Now, the important point here is that all kinds of things can come out of such a collision process, but a process such as this one is also possible. So you have two colliding protons, you have some unknown interaction, and these are two dark matter particles. This Greek letter chi here denotes a dark matter particle. Now, the idea is that you probably can't really see the dark matter particle because they don't interact enough. But still, if you somehow manage to produce them in your Large Hadron Collider, it's quite easy to figure out that they are there if you can account for all the energies of the incoming particles and the outgoing particles that you can see. Okay, so if I know the energies of these two beams that are coming together, and I do know that, and I see a bunch of standard model particles coming out, and I can see these things, I know exactly what energies they have, and I see missing energy, then chances are I've produced some dark matter. Okay? And you can figure out from the way these particles are distributed exactly what kind of mass, interaction strength that these dark matter particles have. So it's all very cool. Now, next thing I want to talk about, that was dark matter. Next thing I want to talk about is the dark energy, which is a different kettle of fish again. And the dark energy is basically this chunk here that makes up more than 70% of the energy budget of the universe. And it's not anything that we know about. I mean, at least the dark matter, okay, it's some non-relativistic stuff, so it's not such a far-fetched thing. But the dark energy is really something else altogether, and it's something that causes the expansion of the universe to accelerate. And this accelerated expansion was first observed by these three guys over here, Brian Schmidt and ANU, and they got their Nobel Prize in 2011. But still, this is just the effect of the dark energy that we know about, the accelerated expansion. We don't really know what exactly this thing is that is causing this acceleration. So we just call it dark energy. As a name, it's a placeholder name. Now, there are many theories around where people try to explain this dark energy, but probably the most accepted, well, maybe accepted is probably the wrong word, but probably the most common solution is to think about dark energy as a kind of vacuum energy. So the vacuum energy is something that is allowed by quantum mechanics. So if you look at the uncertainty principle, this is Heisenberg's uncertainty principle, it says that it's okay to suddenly have particles and antiparticles popping out of empty space. And provided that they annihilate again within a very short time, the time scale allowed by this relation, it's completely fine, okay? And that's what's happening here in this simulation. This is a simulation of the theory of quantum chromodynamics, QCD. That's a theory that is part of the standard model, and it explains the strong force. And these things that are popping out now are the fields, the quarks, the gluon fields within the theory of quantum chromodynamics, and they're just popping out of empty space and then disappearing again. Okay? So that's what we call a vacuum energy. And the question is, now I was telling you before that in GR anything with an energy will gravitate. So the question here is, does this kind of vacuum energy gravitate in the same way as normal energy that we talk about? Because if they do, then it's actually possible to make use of this vacuum energy to accelerate expansion of the universe. Okay, so that's the vacuum energy. Another word about matter-antimatter asymmetry. Okay, so going back to this pie here, so I've explained dark energy and dark matter. Now we move on to atoms. Now you think we think we know atoms, but actually we don't really know them as well as we think. Because if we look around us today, everything is made of matter. Okay, this is matter, I'm matter, you're matter. We don't have any antimatter except at a few colliders. Okay, so what happened? Okay, why is that? Because why should there be more matter than antimatter produced in the universe? Well, it turns out that if you look at the hot Big Bang theory, matter and antimatter were produced in more or less same equal abundance just after the Big Bang. However, there was just a little bit more matter than antimatter. In fact, it's like 1 part in, I don't really know how to count this, it's 10 billion, okay? And as the universe cools and expands, then the matter and the antimatter will annihilate. And what we're left with after annihilation is 1 part in this big number, and that's us. Okay, so the question is, why is it why is it that there's an asymmetry in the first place? It's actually good that there's an asymmetry in the first place, because if annihilation happens and you have equal amount of matter and antimatter, then nothing would exist today. So it's actually good that there is a tiny little bit left over, but the question is why and how. Okay, so this is something that is still a mystery, and probably has something to do with the physics somewhere here at very, very early times. There are some theories around, I can tell you about them later on, but not now. Now lastly, the neutrinos, the last part here. I like the neutrinos. I do a lot of work on neutrinos. I like them a lot. So they're not so strange, because at the end of the day, okay, you don't really know exactly how many neutrinos are there, but still you have an upper limit on the contribution of neutrinos to the energy budget of the universe. But the reason why it is that we only have an upper limit and not an actual measurement is because we don't know the neutrino mass. Okay? We know neutrinos have masses, but we don't know exactly what the mass is. And it turns out that it does matter what the mass is because the neutrino mass has a huge influence on the way structures are formed in the early universe. So here is a simulation I'm showing you of formation of structures with two different neutrino masses. So this is a simulation, as I said. And how do I, there. So you start out with a universe that is essentially homogeneous and isotropic, and then but there's some tiny little fluctuations, okay? And then you let these fluctuations feel each other's gravity, and eventually what happens is that you start developing these filaments and things. So each dot here you can think about as a galaxy, and each structure here is probably something like a galaxy cluster. And the important thing here, comparing these two cases, is that on the left-hand side, we have a case where the neutrino mass is exactly 0. Whereas here, you have a pretty large neutrino mass of 6.9 electron volt. Okay? And you see very clearly that the structures are completely different. Here, you have a lot of really fine details of the structures. Here, you have some gross structure. So like, for example, there's some filaments over here, which is like this thing over here. Similarly, this structure is more or less like this one over here, but you don't have the fine details. And that is what neutrinos do to you. If the neutrinos are too massive, they're going to wipe out all the fine structures in the formation when you form galaxies and galaxy clusters. And that's really powerful because what it means is that if there is such a huge effect due to the neutrino mass on the way structures are formed, then I can conceivably look at, I can conceivably take a galaxy distribution that is from a survey, that I observe from a survey, and then compare that distribution with a simulation like this one and try to figure out backwards what the neutrino mass must be. And that's exactly what's been done by many people. So they look at, this is a galaxy distribution map from the Sloan Digital Sky Surveys in the US. And so you can look at like this distribution of galaxies over here and compare with the pattern that you see from these simulations. And already from this, you can put a constraint on the neutrino mass of 0.25 electron volt. So that's really nice. And actually, that's completely related to the 2% upper limit on the neutrino contribution to the energy budget. So that's everything on the pie. But there are also other fun things that are not on the pie. And I'm going to briefly talk about them. And the first one I'm going to talk about is the origin of fluctuations. So there are fluctuations in the CMB temperature, but still, you have to find out why are there fluctuations in the first place. And it turns out that there's a very powerful theory called inflation that would provide exactly the mechanism to generate the fluctuations that we see in the CMB. And what happens here is that you imagine that you have a field, like a field that is a scalar field, what we call a scalar field, that is permeating all space. And it has a potential. And so what it does is that the scalar field, it starts off at very early times, high up here on the potential. And what it's going to do is to slowly roll down this potential. And while it's slowly rolling down, the dynamics of the field is such that it's going to cause a phase of exponential expansion of the universe. That's the inflation that we're talking about. Okay? And then inflation ends when the field falls down here and it starts oscillating down here and inflation ends. Now the important thing is that this scalar field here is a quantum object, and therefore it can have quantum fluctuations. Like the same kind of fluctuations I was telling you before, the vacuum fluctuations. You could have quanta of the scalar field popping out of in the vacuum. And these quantum fluctuations end up being fluctuations in the space-time manifold or gravitational potentials. And that could give rise to the fluctuations that we eventually observe in the CMB. Another really interesting thing that comes along with the inflation theory is the possibility of fluctuation of space-time itself. Because it turns out that if you have a theory of quantum gravity, so that you can actually have discrete space-time, you can actually quantize it, then you can talk about quantum fluctuations of space-time itself. And it turns out that if this quantum fluctuation, if you have these quantum fluctuations of space-time during inflation, then the inflation process is going to expand these, stretch out these the length scales, these fluctuations to very, very large length scales, and that ends up being possibly observed as primordial gravitational waves. And so that's really exciting, because if you actually manage to detect these primordial gravitational waves, it would be a really strong confirmation that A, inflation happened, and B, you do have a quantum space-time, and therefore a quantum theory of gravity. Now, if you've been following the news in the last year or so, you would have heard about this. That's the spectacular discovery of cosmic inflation by the BICEP-2 instrument, which is in the South Pole. And so basically what we were looking at is the polarization of the cosmic microwave background photons. So I was showing you the fluctuations in the temperature, but you can also make a similar kind of map looking at the fluctuations of the polarization. And if you have primordial gravitational waves, then they will cause the fluctuations of the polarization to form a really interesting pattern. And in fact, you see this kind of curling pattern. That's called B mode. Okay? So the BICEP team claimed that they detected the B mode, and it was all very exciting because everyone thought, whoa, you know, we've got a confirmation of gravitational waves. But just like with the CMB temperature map, where you have a lot of foregrounds that are in front of the actual CMB, the same thing is also true when you're making a polarization measurements. You also have to remove a lot of foregrounds before you can even start talking about the the pattern of the background CMB fluctuations in the polarization. And it turns out that the BICEP team was a little bit too pushing too hard. Basically, they didn't clean their foregrounds well enough. So it turned out that whatever they saw was really just dust in the galaxy. So that was a bit disappointing. It's wrong in the end. But still, you know, the important thing to realize here is that, yes, they didn't measure gravitational waves, but it doesn't rule out inflation, because in inflationary theory, there's actually no fixed amplitude for the gravitational wave background. So it could be that the gravitational wave background amplitude is just too small to be detected. So it doesn't rule out inflation, so it's all fine. But anyway, it's a bit disappointing, as said. So yeah, I think I'm going to be wrapping up, and I'm just going to leave you with this picture. So thanks for your attention.